Start with a single point of light. Not a star, but something far older and far stranger than any star you will ever see with your own eyes. It is a galaxy. The light we are gathering from it tonight set out on its crossing 13.5 billion years ago, which means it left before the sun caught fire, before the Earth gathered itself out of a slow-turning cloud of dust and ice, before the atoms that would one day be arranged into you had been forged in the hearts of stars not yet born. When that light began to travel, the whole universe was less than 300 million years old, an infant by every measure we knew how to take. And the galaxy that sent it was already enormous, already brilliant, already salted with oxygen, the ash of stars that had lived and died and scattered themselves back into the dark so that something new could be built out of the pieces. By everything we thought we understood, it should not have been there. Not yet. For almost the whole of human history, we could not have known such a galaxy existed, because we had no way to see it. Its light is faint past the edge of meaning, stretched thin and reddened by the long fall through an expanding universe, carried so far out of the visible and into the infrared that no human eye and no ordinary telescope could ever catch it. To find it, we had to build something that had never existed before. In the last days of 2021, we folded a mirror of gold and beryllium wide as a house into the nose of a rocket. We flung it 1.5 million kilometers out past the moon, and we let it settle there in the cold and the silence until it was still enough and cold enough to hear the faintest and oldest light there is. We named it the James Webb Space Telescope. When it opened its eye in the summer of 2022 and turned to face the beginning of everything, it found that the beginning was not the empty, patient darkness we had pictured. It was crowded. Consider what that eye can do. Point it at a scrap of sky so small you could hide it behind a single grain of sand held at arm's length. Let it hold perfectly still for half a day, and thousands of galaxies rise up out of the black, most of them far older than the Earth, some of them nearly as old as time. We had imagined the young universe as a slow place, a long, dim morning in which the first faint galaxies were only beginning to gather and flicker, taking their unhurried time. That is not what came back. One after another, galaxies resolved out of the dark that were too large, too luminous, too far along, and their hundreds of millions of years too soon. The telescope kept finding them deeper and deeper in time, each more distant than the last, and each one, stubbornly, still bright, still substantial, still there. The single galaxy we began with, the most distant one we have so far confirmed, spreads across more than 1,600 light-years and burns with the gathered light of something close to 500 million suns, and it manages this in a universe younger than the gulf of time that stands between you and the last of the dinosaurs. When the astronomers measured the heavy elements threaded through that early starlight, they reached for a homely comparison. It was, they said, like walking into a room you expected to be full of newborns and finding a grown adolescent instead. You can feel the shape of the problem well enough without a single equation. Galaxies take time. It takes time to draw the gas together, time to kindle the first stars, time to let those stars burn through their lives and die, and seed the darkness with the elements that make the next generation richer than the one before. That slow, layered building was the story we thought we understood. A tide coming in across the first billion years, and here was the universe, only a few 100 million years past its own beginning, handing us galaxies that looked like the work of ages. So the people who spend their lives on these questions did the honest thing. They admitted they were confused. In the pages of careful journals, some of them began to wonder aloud whether we had misread something fundamental about the way the universe put itself together, whether the first light was quietly telling us that our whole account of the beginning was wrong. That is what these long hours together are really about. Not a catastrophe and not a broken universe, but a true and genuinely beautiful puzzle. The kind that only arrives when a new instrument lets us look hard at something we were never able to look at before. How do you grow a finished galaxy in a universe that has not yet had the time to grow one? What were we missing? And what has this ancient light been trying to tell us all along, through the long stretch of years when we still lacked the eyes to read it? There is something almost unbearably strange about the fact that we get to ask these questions at all. For 13 billion years, the universe made its galaxies and its stars, and slowly forged the heavier atoms, the oxygen, the carbon, the iron, that would one day let a small wet planet grow something able to wonder. It did all of that with no one there to see it. And then, in the last thin sliver of that long history, the seeing began. We are, as far as we have ever been able to tell, the part of the universe that turned around to look back at where it came from. When we finally looked and found the beginning busier and brighter and stranger than we had any right to expect, there was a kind of grace hidden even in that. To be surprised by your own origins is to still be paying attention. So before we travel back toward that beginning, all the way back to the first few 100 million years, to the light that started all of this, settle in. Get comfortable. There is nothing here you have to solve tonight. You can simply come along and listen, and let the story carry you wherever it goes. If you find yourself drawn along by these quiet nights, you might think about subscribing so we can keep taking the long way through the universe together. And before we begin, tell us one thing, if you would. Where are you listening from, and what hour is it there? Leave it below if you feel like it. There is something steadying in picturing all of us at once, scattered across the night side of a slowly turning planet in 100 cities and 100 different hours, each of us leaning toward the same impossibly old light. Because that is the quiet marvel underneath everything we are about to follow. Before we can be astonished by a galaxy that arrived too early, before we can ask what it means or what it says about us, we have to be able to trust that we are truly seeing it. That a faint smudge of infrared can be read like a letter and believed, and to understand how that is even possible, how a machine can look not merely across the width of space but backward into time itself, we have to start not at the dawn of the universe, but with the strange and patient thing we built to find our way there. You have never once seen anything as it truly is, only ever as it was. It is easy to forget, because on the scale of a single room, the delay is far too small to notice. The face of someone across the table reaches you a fraction of a heartbeat late. The far wall arrives a shade later than the near one. Light is fast, but it is not instant, and everything you see is a message that took some amount of time to cross the distance to your eye. Widen that distance and the delay grows teeth. The sun you picture warming the afternoon is already 8 minutes out of date. If it was snuffed out, you would go on standing in its light for 8 more minutes before the sky ever knew. The next nearest star is 4 years gone by the time its glow finds you. And a galaxy out near the faint edge of the sky is not minutes or years, but millions, sometimes billions of years old before its light ever lands on a mirror. Which means a telescope aimed at that faint edge is not really an instrument for looking far away. It is an instrument for looking into the past, the only kind of time machine the laws of physics actually permit. Point it far enough, and you are no longer watching the universe as it is. You are watching it in its childhood. But there is a catch, and it is the reason the deepest past stayed hidden for so long. As that ancient light crosses the universe itself is stretching. Every reach of space slowly swelling, carrying every galaxy away from every other, and the light is drawn out along with it. Its waves are pulled longer and longer as they travel, and the color of light is nothing more than the length of its waves, so the light slides steadily down the spectrum on its way to us, from blue toward red and then past red altogether, out of the narrow band your eyes can register and into the infrared, into what is, in plain terms, heat. Astronomers call this stretching redshift, and it means the oldest light in the universe does not reach us as anything we could see. It reaches us as a warmth so faint that catching it took an eye built for nothing else. It is why the great telescopes that came before, for all their genius, simply could not reach the first galaxies. That light had been drawn clean out of the visible, and no ordinary eye can see heat. To catch a warmth that faint and that old, you need an eye that is very large and very cold and very far from home. Large, because faint light is a question of how much you can gather, and the wider the mirror, the more of that thin, ancient warmth it can pull in. Webb's mirror is 6.5 meters across, far too big to fit inside any rocket in one piece, so it was built instead as 18 separate hexagons of beryllium, a light and rigid metal locked edge to edge into a single honeycomb, folded up like origami to fly, and then unfolded, panel by panel, out in the dark. Each hexagon is finished with a film of gold only a few hundred atoms thick, because gold, of all the metals, makes the finest mirror there is for infrared light. And yet, for all the size of the thing, the total gold spread across that entire mirror, gathered into one place, would come to about the volume of a marble. Cold, because heat is precisely what this telescope is trying to see, and anything warm glows in the infrared, including the telescope itself. An instrument hunting faint heat while radiating its own is like trying to photograph a single candle from inside a burning house. Its own glare erases everything worth seeing. So, Webb rides behind a sunshade the size of a tennis court, 5 gossamer layers of it, held at an angle that keeps the sun, the earth and the moon all on one side, always, while the mirror waits in permanent shadow on the other. There it cools to around 40 degrees above absolute zero, close to the coldest temperature that can exist anywhere. And one of its instruments, built to catch the longest and faintest heat of all, is chilled further still to only a few degrees above that final floor. And far, because distance is what keeps all of that warmth safely behind it. Webb does not circle the Earth. It sits about 4 times farther out than the Moon, at a quiet balance point in the sky where it can hold its position, tucked behind its own shadow, undisturbed by the heat of home. Put those 3 together, large, cold and far, and the eye becomes almost unreasonably sensitive. Sensitive enough, the people who built it like to say, to feel the body heat of a single bumblebee at the distance of the Moon. That is the instrument we finally turned toward the first light. It does 2 different things with what it gathers. First, it finds. A camera sweeps across a patch of deep sky and picks out the faintest red specks scattered through it. The candidates, the smudges that might be galaxies from the first few 100 million years, or might be something nearer and duller wearing the same color. On its own, a speck's color can fool you, so then it confirms. A second instrument takes a single galaxy's light and spreads it out into all its separate wavelengths, the way a raindrop opens sunlight into a band of color, and written across that spread is the real signature. How far the light has been stretched, and so how deep in time it comes from, and which elements were burning to make it in the first place. A guess becomes a measurement, a smudge becomes a distance, and an age, and a chemistry. So when Webb settles onto one of those faint red points and reads it, the thing it is doing is stranger than any story of time travel. It is not seeing the galaxy. The galaxy, if it endures at all, is long since changed, grown old, or drawn into something larger, or scattered back into the dark. And whatever it has become, that news is still in transit and will not reach us for ages yet. What the telescope holds is only the light the galaxy let go of when it was young, a portrait of a single moment, 13 billion years gone, still crossing the emptiness. We do not look at the early universe. We receive it like a letter that outlived the hand that wrote it. And an eye like that, for all its brilliance, still only shows you the light. It cannot tell you what the light was supposed to be, whether a particular galaxy is ordinary or impossible, expected or astonishing. That judgment comes from somewhere else entirely, from the map you were already holding when you looked. Long before Webb ever left the ground, we had drawn that map in careful and confident detail, a full account of what those first few 100 million years ought to contain, how empty they should be, how slowly the light should come. And to feel why what came back unsettled us so deeply, we have to unfold that map first and read it the way we once believed it, back before the first light began, ever so quietly, to disagree. We did not go into the dark blind, for all that the early universe hides from us. We were not guessing when Webb finally turned toward it. We carried a story, a careful one, built up over most of a century and tested against nearly everything we could measure. And that story told us, with real confidence, what the first few 100 million years were obliged to look like. It is worth reading that story the way we believed it, before the light arrived to argue, because for a very long time it worked. It begins in heat. The young universe was so hot and so crowded that atoms could not hold together and light could not travel far. It was a glowing fog everywhere at once, brilliant and blind. Then, as everything expanded, everything cooled, and at about 380,000 years old, the universe crossed a threshold. It grew cool enough, at last, for the loose particles to settle into the first whole atoms, and in that moment, the fog lifted. Light that had been trapped and scattering forever was suddenly free to fly in straight lines across an open, transparent cosmos. That light is still arriving. It fills all of space, stretched by all the time since into a faint hum of microwaves, the oldest light there is, the far edge of everything we can see. You have even met it yourself, without knowing. A small part of the grey fizz that used to wash across an untuned television was exactly this, the cooled afterglow of the beginning, now barely 3 degrees above absolute zero. And then, having set that first light free, the universe went dark. This is the long stretch we call the Dark Ages, and it was genuinely dark. Not a single star anywhere, no galaxies, nothing burning at all. Only the plain hydrogen and helium the Big Bang had left behind, spreading and cooling and drifting through a silence that lasted longer than it is easy to hold in the mind. Had you been there to look, there would have been nothing to see. Only gas and gravity and time. But gravity is patient, and it was already at work. Threaded invisibly through all that gas was something else. Dark matter, the great unseen majority of all the matter there is, which neither shines nor blocks light, but pulls on everything the same. Take all the matter in the universe, and only about 1 part in 6 of it is the ordinary kind, the stuff of gas and stars and planets and people. The other 5 parts are dark, known only by their weight. And that dark matter, faintly clumped from the very beginning, began to gather itself into vast unseen wells. The ordinary gas drawn by that gravity came trickling down into the wells after it, pooling and thickening and growing denser at the centers, until somewhere in that dark a knot of gas grew hot and heavy enough that its core caught fire. The first star, a single new point of light in a universe that had never held one. And around it, the first small clusters of stars that would one day be called galaxies. Everything about that picture said the same word, over and over, slowly. Structure was meant to build from the bottom up, small things first, and only later, through patient gathering and merging, the large. A great galaxy was never born whole. It was assembled, clump onto clump, across hundreds of millions and then billions of years. So the first few 100 million years, the map insisted, should be a thin and modest time, a scattering of faint, small, half-built things just beginning to glow, and little else. And we had every reason to trust that map, because it was not a hunch. The same theory that predicted this slow, bottom-up building also predicted the exact pattern of faint ripples frozen into that ancient afterglow and the vast web of galaxies strung across the sky around us today. And when we checked, both matched beautifully. This was one of the best tested ideas in all of science. The map insisted on one more thing, quieter but just as firm: a ceiling. A galaxy cannot conjure stars out of nothing. It can only build them from the ordinary matter it has managed to gather, that one part in 6. And even then, it is wasteful, turning perhaps a 10th or a 5th of that gas into actual stars before the winds and explosions of the first stars blow the rest away. So there was a hard limit on how much a young galaxy could possibly be. Whatever the first light eventually showed us, it was not supposed to show us grown, blazing, heavy galaxies. This early, there simply was not enough of anything to build one. To feel how early the first few 100 million years really is, shrink the whole life of the universe, all 13.8 billion years of it, down to a single calendar year. On that scale, the Big Bang is the first instant of the 1st of January. The oldest light, that afterglow, breaks free about a quarter of an hour later, still in the small hours of New Year's Day. The dark ages fill the opening days of the month, and the galaxies at the very heart of this story, the earliest ones Webb would go on to find, flicker into being within the first week or so of that year, while the universe is, by every measure, still a newborn. The sun does not catch light until the beginning of September. The Earth gathers just after. The last of the dinosaurs die on the 30th of December, and the whole of written human history, every empire, every name you have ever heard, fits into the final few seconds before midnight on the 31st. That is where the first galaxies live. Not in the deep past of our world, but in the deep past of the universe itself, in the opening days of the cosmic year. This was the schedule we were confident the universe had kept. It was sensible, it was tested, it agreed with the afterglow and the gas and the slow arithmetic of gravity, and, to be fair about it, you would very likely have drawn it the same way, with the evidence we had. Then, in the summer of 2022, we aimed that cold golden eye at the first days of the cosmic year, and hour by patient hour began to gather the light. And almost at once, gently at first, and then not gently at all, the map and the light began to disagree. First over a single galaxy sitting where the map had promised almost nothing, and then over another, deeper still, and then another beyond that. For years, the most distant galaxy we knew went by a plain catalogue tag, GN-Z11. It was Hubble's champion, the deepest thing the older telescope ever managed to reach, a faint smudge tucked into a well-studied patch of northern sky. Hubble could not truly measure it. It could only estimate, from the galaxy's colours, that its light had been stretched by a redshift of about 11, which would set it around 400 million years after the Big Bang, further into the dawn than anything else we had ever seen. And it was oddly bright for something so far away, brighter than a galaxy that Young had any obvious right to be, though at the time that was filed away as a curiosity rather than a warning. The estimate was bold enough and became famous enough that it wrote itself into the galaxy's very name. The 11 in GN-Z11 is that redshift, the guess stamped directly onto the thing itself. Then Webb turned its cold eye on the same smudge and did what Hubble never could. It spread the galaxy's light into a full spectrum and read the true stretch, line by line. The measurement, when it came, was both a triumph and a quiet correction. The galaxy was real, and it was genuinely ancient, but not quite as far as the guess had claimed. Its redshift was not 11, but 10.5. Its light let loose a little later than we had thought, some 430 million years after the beginning. It had been wearing a name that no longer quite fit. And that, in miniature, was the lesson the whole coming flood would teach over and over, that a colour is a guess and a spectrum is a fact, and the two do not always agree. What happened next still has the feel of a dam giving way. For decades, the record had crept outwards slowly, a single, hard-won rung every few years. Webb overturned that pace almost the moment it opened its eye. Within months, a deep survey named Jades, a long, patient stare into one much-studied patch of the dark, turned up not one ancient galaxy, but 4 of them at once, each drawn out of the same small square of sky, and confirmed everyone with a real spectrum. 4 galaxies, all measured, all beyond a redshift of 10, where a single season earlier there had been none. The astronomers watching the data come down could barely keep pace with their own instrument. The frontier that had inched along for a generation was suddenly in free fall, and the 4 of them made a ladder. The shallowest sat near GN-Z11 at about 10, but the rungs dropped away from there, 11.5, then 12.5, and the deepest at a redshift of 13, its light set free when the universe was only 325 million years old. 4 steps down into the first light, and not one of them a candidate to be argued over, but a galaxy confirmed, its distance spread out and red. That word, confirmed, mattered even more than the records did. Anyone can find a faint red speck and suspect it is far away. The hard and honest thing is to prove it, to gather enough of that thin light, spread it, and find in the spreading the unmistakable signature of an enormous stretch. These were the first galaxies beyond a redshift of 10 for which we held that proof rather than a hopeful guess. And the difference would only grow more important as the frontier fell deeper, because the deeper you reach, the fainter the light becomes, and the easier it is to be fooled by something much nearer, wearing the same red that distance wears. It is worth pausing on what climbing down this ladder actually means, because it is stranger than it sounds. Each rung is less a place farther away than a moment further back. To fall from a redshift of 10 to a redshift of 13 is to drop from 400 million years after the beginning to barely 300. To watch the universe grow younger as you descend, rather than older. At that deepest rung, you are seeing the cosmos when it had lived out only about 2.5% of its life. More than 97 parts in 100 of everything that has ever happened had not yet happened. No sun, no earth, no ocean, no first living cell, and no word for any of it, because there was nothing anywhere to do the naming. By the time that light set out toward us, not one thing you have ever seen or touched or loved had begun to take shape. And it fell, unbroken, through an expanding dark for 13 billion years, to arrive at last on a mirror the width of a house. For a while, the wonder of the descent was enough all on its own. We were looking further into the beginning than anyone ever had, and each new rung was a small triumph of engineering and patience. But somewhere in the falling, a second feeling settled in beneath the awe. The map had promised that this deep, this early, there should be almost nothing, a thin scattering of faint, half-built sparks, dim and barely holding together. And these galaxies were not quite behaving that way. They were there too readily, too surely, holding their shape and holding their light with a steadiness the first few 100 million years were never meant to allow. Still, a bright galaxy at a redshift of 13 is something the mind can stretch to hold. So the ladder kept dropping, rung after rung, further than seemed reasonable, until, one step deeper than all the others, it came to rest on the faint red light we began with, hours ago, at the start of this night. And when we finally stopped falling and held still and looked at that one closely, the record quietly stopped being a record. It became a problem. So we stopped, and we turned all that patient machinery onto a single faint smudge and looked at it hard. It was the galaxy we began with tonight, a few grains of infrared light, easy to overlook. But when Webb studied it closely, and then a second telescope studied it after, that smudge gave up 3 separate facts about itself, and every one of them was a quiet impossibility. We met all 3 in passing at the very start of this night, that it was wide, that it was bright, and that it was steeped in oxygen. It is worth returning to them now, one at a time and slowly, because each is a door into the same astonishment. Begin with wide. When you find something blindingly bright in the early universe, the usual explanation, the almost boring one, is a quasar, the glare of a giant black hole swallowing gas at the heart of a galaxy, an engine so violent it can outshine everything around it from a region no larger than our own solar system. And the giveaway of a quasar is that it is a point. All that light pours from a single tiny core, so however far away it lies, it shows up in the image as one unresolved speck, sharp as a star. This galaxy is not a speck. When Webb resolved it, made out its actual shape rather than a dot, the light was spread across more than 1,600 light-years of space. And light that is spread out cannot be pouring from one pinpoint engine. It has to be coming from many separate sources, scattered across a real breadth of sky, from stars, hundreds of millions of them, strewn through a genuine galaxy 1,600 light-years wide, burning all at once when the universe was less than 300 million years old. That is the hinge the whole story turns on. This was no black hole dressed up in a galaxy's clothes. It was the thing itself. It helps to try to stand inside it for a moment. Picture a galaxy far smaller than our own, but crowded. Thousands upon thousands of young, hot, blue-white stars packed into a bright and restless body, so many and so near one another that the gas between them glows. New stars are catching fire across it constantly, faster than almost anywhere in the universe today. There are no old, calm, yellow suns like ours anywhere in it. There has not been the time for such a thing to exist. Everything is young and blue and burning fast. That is what was there, all 1,600 light-years of it, when the cosmos was barely out of its own beginning. Then bright. Even once you grant that it was built of stars, there were simply too many of them, and they burned too hard. It ranks among the most luminous galaxies anyone has found at that depth, forging new stars at something like 25 suns worth every single year, crammed into a body a fraction the size of our galaxy. The schedule had promised a few dim, struggling sparks this early. Here instead was a furnace. And then oxygen, the strangest of the 3, and the one that took that second telescope to settle. High on a plateau in the Chilean desert, so dry and so high it is nearly off the world, sits a great ring of linked radio dishes called ALMA, built to catch light with wavelengths even longer than Webb can see. When ALMA turned toward this galaxy, it caught the unmistakable glow of oxygen in its gas, and in the process it fixed the galaxy's distance with a precision that is genuinely hard to picture, something like measuring out a full kilometer and being sure of it to within 5 centimeters. But the precision is not the real surprise. The oxygen is. Oxygen is not something the Big Bang knew how to make. The young universe arrived with only its 2 lightest ingredients, hydrogen and helium, and nothing heavier at all. Every single atom of oxygen that exists was cooked in the core of a star and then flung out into space when that star died. So for a galaxy to be laced with oxygen, whole generations of stars must already have been born, burned through their lives and died, seeding the gas around them with their ash. All of it inside 300 million years. The stars that made this oxygen were already gone by the time the light left. Part of what we are looking at is a monument to a first generation that had lived and died before the picture was even taken. It was, as the team said plainly when they announced it, like stepping into a nursery expecting a newborn and finding a teenager. This galaxy was not only large and bright far too soon, it had grown old far too soon. What makes all of this so hard to wave away is how certain it is. These were not hopeful colours with a distance penciled beside them. Webb spread the galaxy's light and read its stretch directly. Alma found the oxygen and pinned that same distance to a hair's width. Two very different instruments, working in two very different kinds of light, arrived at the same answer. Whatever this galaxy is trying to tell us, it is not an error, and it is not going to dissolve on a second look. It did not even come alone. Right beside it, at very nearly the same enormous distance, Webb found a companion, fainter, perhaps a tenth the weight, and this one a compact point rather than a resolved sprawl. Two galaxies, shoulder to shoulder at the edge of sight, one a spread-out giant of stars, the other a tight, dim knot of light. Already the early universe was showing us that it came in more than one kind, and that some of its lights were points after all, a detail worth holding on to. Nor did the frontier stop there. Within a couple of years, the record slipped deeper still, to a galaxy turned up by a survey bearing the almost too fitting name Mirage or Miracle, a name that asks precisely the right question of everything out at that distance. It sits at a redshift of about 14.5. Its light released some 280 million years after the beginning, and as of tonight it stands as the most distant galaxy our species has ever confirmed. Nothing beyond it has been pinned down. A handful of fainter candidates drift further out, unconfirmed and easy to doubt. For now, that galaxy marks the edge of seeing, the deepest we have yet reached, and it too shone brighter and turned up far more often than it had any business doing. Lights like it should have been almost absent at that moment in cosmic history, and instead Webb kept finding them, something on the order of 180 times more frequently than the models had ever left room for. So hold it in your mind a moment, because it repays the holding. A real galaxy, hundreds of millions of stars, 1,600 light-years across, blazing away and already seasoned with the ash of the dead, fully grown and shining when the whole universe had existed for less time than a 15th of the age the Earth has reached today. Not a trick of the light, not a black hole in a costume, but a grown thing, fully itself, in a newborn cosmos. One galaxy like that is a wonder, the kind of paradox you can sit with on a quiet night and simply turn over in your hands. But it was never going to stay one galaxy. And the real alarm, when it finally came, did not rise from the deepest, faintest rung of the ladder at all. It came from a little nearer in, from a small crowd of galaxies that were not merely early, but impossibly, unaccountably heavy. 6 of them all at once. In the week the word broken first reached the headlines. The deepest galaxies had startled us with their light. The 6 that came next startled us with their weight. They were not new records for distance. They sat a little nearer in than the faint red edge we had been falling toward, at redshifts of 7 and 8 and 9, which places their light somewhere around 500 to 700 million years after the beginning, later than the galaxy we opened the night with. In the deep images they were easy to overlook, small, deep red and unremarkable. But when a team of astronomers, led by a researcher named Ivo Labbé, measured how much starlight was pouring from each of these 6 little smudges, and worked out how many stars it would take to make that much light, the numbers stopped them cold. Several of the galaxies seemed to hold tens of billions of suns worth of stars. One of them looked to hold close to 100 billion, very nearly the entire mass of stars in the Milky Way, the whole broad spiral we live inside, somehow already gathered and shining when the universe was only a few 100 million years old. It is worth saying how little they looked like a catastrophe. In the images they were nothing, half a dozen dim, ruddy dots, the kind of thing the eye slides over without a second thought, indistinguishable at a glance from 1,000 ordinary distant galaxies. All of their menace lived in the arithmetic. You could not see that these were monsters, you could only calculate it. And that somehow made them more unsettling rather than less, the universe apparently breaking its own rules quietly in objects too modest to draw any attention to themselves. Because weight is a harder kind of problem than brightness. A galaxy can be briefly, freakishly bright. A sudden burst of new stars can flare and then fade. But mass is not a flash, it is a sum. 100 billion suns worth of stars is 100 billion stars worth of building, of gas gathered and cooled and lit, one generation laid down after another, and all of that takes time. And it takes raw material, which is exactly where these 6 galaxies ran headlong into the ceiling. Recall the limit the map had drawn. A galaxy cannot make stars out of nothing. It can build them only from the ordinary matter it has managed to gather, and ordinary matter, the stuff of gas and stars, is just about 1 part in 6 of all the matter there is. The other 5 parts are dark and make no stars at all. And no galaxy is even close to thorough about the fraction it does have. Everywhere we can check, galaxies turn only 1/10, perhaps 1/5 of their available gas into stars before the rest is blown away or heated past use. That is the rule in every corner of the universe we have ever measured. So someone ran the arithmetic, a kind of stress test on the whole standard picture, and asked a plain question. To build the heaviest of these 6 galaxies, this early, how efficient would the universe have needed to be? The answer was almost comic in its extremity. It would have had to take very nearly all of the ordinary matter within reach, around 99% of it, and turn nearly all of that into stars, wasting close to nothing. Not the 10th or the 5th that galaxies manage everywhere else, but the entire supply. And that is not merely a high number, it is a physically implausible one. It is like being told that someone built a cathedral by hand, using every last stone quarried for 100 miles in any direction and leaving not one behind, and finished it before they were old enough to leave school. So there were only ever 2 ways to read the 6 universe breakers, and both could not be true. Either these galaxies were exactly as heavy as they appeared, in which case our whole understanding of how the cosmos assembles its galaxies, patient from the bottom up, hemmed in by that hard ceiling, was badly and fundamentally wrong. Or the measurements were wrong. There was no comfortable ground in between. And in the early months of 2023, it was the first reading that took the world by storm. You can feel why. There is something in us that thrills and recoils in the same breath at the idea of a rule being broken at the deepest possible level, and this was as deep as rules go. The headlines nearly wrote themselves: Galaxies too big to exist. The James Webb Telescope breaks cosmology. The team themselves had reached for that same register. They nicknamed their 6 red smudges the universe breakers, and observed, not without a certain awe, that these objects stood in tension with 99 of every 100 models anyone had ever built of the early cosmos. For a stretch of months, in seminar rooms and in the pages of careful journals, thoughtful people said the once unsayable thing out loud. What if the standard story of the universe was simply wrong? It was a genuine cliff edge, and it deserves to be remembered as one. But underneath all the alarm sat a single quiet word, load-bearing and easy to miss. And the astronomers who found the galaxies had put it there themselves, in careful print. If. if these masses could be verified with spectra. Because, and by now this ought to ring a bell, every one of these 6 galaxies was still only a candidate. Their staggering weights had been estimated from colour, from the broad shade of their light, and not yet read from a true spectrum. A colour is a guess. It is often a fine guess made by careful people, but it is a guess all the same, and the entire towering crisis was balanced on 6 of them, not one yet checked. That single doubt would come to matter more than almost anything else in this whole story. But before anyone could put these galaxies to the harder test, the 6 universe breakers were already holding out a clue, one that had been lying in the open the entire time. They were red. They were oddly small, tight little knots of light rather than broad sprawls. And once astronomers knew what to look for, there turned out to be not 6 of them, but a great scattering, far more than anyone had ever thought to count. Once you have learned to see one, you begin to see them everywhere. Go back through Webb's deep images with the 6 universe breakers in mind, small, compact, deeply red, and the same kind of object starts surfacing all across the early sky. Not 6 of them, but hundreds. Tiny crimson points, scattered through the first billion years of the universe, like a slow scatter of red embers across the dark. So numerous and so alike that they plainly were not a fluke, but a population. A whole class of thing nobody had known to name. So they were given a name about as plain as they look. The little red dots. And they came with a curious habit. They crowd the young universe, most common somewhere in its first 1 billion or 2 years. And then, as cosmic time runs on, they thin and vanish. Long before the universe is anything like grown, they are essentially gone from the record. A sky that fills with these red points, and then, over the ages, quietly empties of them. Whatever they were, they belonged to the young cosmos, and very nearly to the young cosmos alone. Their light carries a signature you never see in an ordinary galaxy. Spread it out, and it makes a kind of shallow V, steeply, deeply red, invisible light, then crossing over into the ultraviolet, turning abruptly blue again, with a sharp step in the middle where one behavior gives way to the other. That bent, two-sided shape became the fingerprint. If a faint point of light showed that particular kink, it was one of them. And the whole mystery of these objects lives inside that shape, because there were 2 very different ways to read it, and each led somewhere astonishing. The first was stars, an unimaginable density of them. Pack enough old red stars into a small enough volume, the reasoning went, and you could squeeze that deep red glow out of a single compact point. This was the reading that had made the universe breakers so heavy. If all that red light was starlight, then behind each little dot sat a colossal mass of stars, tens of billions of suns crammed into almost nothing. On this account, the little red dots were the most extreme galaxies in all of creation. The other reading was a black hole. Not stars at all, but the glare of a supermassive black hole feeding, gas spiraling inward, heating, blazing as it falls, the same violent engine that lights a quasar. And when astronomers took careful spectra of the little red dots, they found the exact mark of that. Broad emission lines, the light of gas smeared across a wide span of speeds, as though racing around some central mass at thousands of kilometers a second. That smearing is the signature of a black hole's grip, and it turned up in very nearly every little red dot anyone was able to test. The verdict tilted hard. These were not, for the most part, colossal knots of stars. They were black holes feeding, in the first 1 billion years, thousands upon thousands of them, except that they refused to behave like black holes. A supermassive black hole feeding hard is one of the loudest things in the universe. It should pour out X-rays. It should heat the dust around it until that dust glows in the mid-infrared like a live coal. The little red dots do neither. Aim an X-ray telescope at one and you get, in most cases, silence. search for the warm glow of dust, and it simply is not there. Somehow they were black holes that did not shout in X-rays and did not radiate heat, feeding engines with the volume turned all the way down. That was not supposed to be possible. The idea now gaining ground, and it is worth stepping carefully here, because this is a story still being written, is that a little red dot is a black hole in disguise. Picture a feeding black hole wrapped in a cocoon of gas so thick, so dense, that the gas itself begins to glow like the outer skin of a star. That shroud swallows the black hole's fierce X-rays before they can escape, muffles its violence and re-emits the energy softened and reddened, producing from the outside exactly the strange red light and the bent V-shaped signature we see. They gave it a name that holds the paradox whole, a black hole star, a thing that is a black hole at its heart and shines like a star at its surface. The clues have been mounting. One little red dot, nicknamed the cliff for the steep drop in its light, shows a step so sharp and so deep that no assembly of stars, however arranged, can produce it. But a shell of dense gas around a central engine can with ease. And there was a further humbling twist. If the broad smear in their light comes not from gas orbiting at tremendous speed, but from light ricocheting through that dense fog on its way out, then the black holes inside are far smaller than we first calculated, perhaps 100 times smaller. By the middle of 2026, the people who run the telescope were calling this the strongest evidence yet that black hole stars are real. And almost in the same breath, the researchers themselves were saying the honest thing: give it another year or two. One prominent astronomer went further still and wondered aloud whether the little red dots are even a single kind of object at all, or several different things that only happen to look alike. But set the uncertainty aside for a moment and follow the consequence, because this is the first real crack in the whole crisis. If the red glow of these objects is mostly a shrouded black hole and not a vast throng of ancient stars, then the enormous stellar masses we had calculated for them were counting the wrong light. We had read the glare of a single black hole as though it were the combined shine of 100 billion suns, the sort of mistake you could make yourself, taking one fierce lamp behind a sheet of frosted glass for a whole room full of candles. Take the black hole's contribution away, and much of the impossible mass simply evaporates. It was never 100 billion stars. It was light dressed as stars. It is a quietly unsettling thing to sit with, that what looks solid, a whole galaxy's worth of matter, can turn out to be an illusion of how the light was read. The universe had not necessarily broken any rule. We had, perhaps, misread the evidence. And yet an answer like that never shuts a case cleanly. It opens a stranger one behind it, because a black hole heavy enough to outshine a galaxy, sitting there in the first billion years, even a smaller one than we had thought, even one draped in glowing gas, is an impossibility all its own. Black holes are not born large, they have to grow, and growing takes time, which is the one thing the early universe did not yet have. So the little red dots handed us their red light with one hand, and with the other passed us a harder question than the one they had just answered. How do you build a black hole that big, that early, that fast? The question was not hypothetical, and that was the trouble. If the little red dots had only raised the possibility of early black holes, other objects removed the doubt entirely. Webb, sometimes working alongside an older X-ray telescope named Chandra, kept turning up supermassive black holes deep in the first billion years, not candidates this time, but confirmed, their gravity written unmistakably into the light of the gas racing around them. And once you began tallying up their weights, a familiar unease came back. They were too big and too early, and sitting in entirely the wrong place in the story. Take one of the first that Webb pinned down, a black hole shining at a redshift of nearly 9. Its light set loose around 570 million years after the beginning. Weigh it, and it comes to about 9 million suns. That number should feel oddly familiar, because it is roughly the scale of the black hole at the center of our own galaxy, the one crouched at the heart of the Milky Way, Sagittarius A star, some 4 million suns of it, around which the whole slow pinwheel of our stars, our own sun and this planet, and you along with it, quietly turns. A black hole about twice that mass, fully grown, was already anchoring a galaxy when the universe was barely 4% of the age it is now. And that was one of the smaller ones. The earliest black hole we have yet confirmed with a spectrum sits at a redshift of about 9 as well, and it too turned out to be one of the little red dots, a black hole muffled inside its glowing shroud. At the far end of the range waits a genuine monster, found before Webb ever flew, a blazing quasar whose central black hole already weighed 1.5 billion suns just 670 million years after the Big Bang. A billion-sun black hole in a universe not yet finished with its first billion years. But the raw weights were not even the strangest part. It was the proportions. In the universe around us, there is a tidy rule. A galaxy and the black hole at its center grow up together, and the black hole ends up small, about 1 part in 1,000 of all the stars around it, a heavy full stop at the end of a long sentence. Big galaxy, proportionally little black hole, wherever we look. In the early universe, that rule is turned on its head. These black holes are overmassive, not 1,000th of their galaxies, but 100th, 1/10th, and in the most extreme cases, very nearly the whole of it, a black hole that rivals the entire mass of stars surrounding it. It is as though the order of events had been reversed, the black hole coming first, and the galaxy gathering around it only afterward. The seed before the tree, the heart grown before the body it was meant to beat inside. Which brings us to the real difficulty, the one astronomers call the seeding problem, and it comes down to a race against a clock. Black holes grow by feeding, and feeding has a speed limit. Pour gas onto a black hole too quickly, and the heat and light of that infalling matter push back, blasting the rest away before it can be swallowed. So even gorging at the maximum steady rate, a black hole can only multiply its weight by about 2 or 3 every 40 million years, a doubling and a doubling and a doubling patiently across the ages. Now start the clock. Take the most natural seed you can picture, the black hole left behind when one of the very first stars collapsed and died, a corpse of perhaps 100 suns, and let it feed flat out, without pause, for every year available to it. Do the arithmetic, and you find that even under those perfect, ceaseless conditions, it can barely claw its way to 1 billion suns in the time before that ancient quasar was already blazing. The black hole should lose the race, and yet there it is. Somewhere, something had to cheat. Physicists have proposed 3 ways it might have. The first is patience and sheer numbers. Perhaps the small seeds, the dead first stars, were simply everywhere, and a lucky few, sitting in the richest currents of gas, fed almost perfectly from the very beginning. The second is a shortcut, and it is the favorite for the overmassive ones. Skip the star altogether. Under the right rare conditions, a vast cloud of pristine gas might collapse straight into a black hole all at once, a whole sun's worth of material, and far more, falling inward and simply going dark instead of catching fire, handing the black hole a running start of 10,000, even 1 million suns, born big and already outweighing whatever galaxy would later gather round it. And the third way is just to break the speed limit, to feed in short violent bursts faster than the steady rule should permit. We have caught early black holes doing precisely that, one out near the edge of the record, feeding at perhaps 5 times the supposed maximum, gorging while the gas holds out. None of these is settled. Different black holes may well have taken different roads. It is, in the most honest sense, an open case. and it is worth being honest about just how open. For a while, the single strongest piece of evidence for the Bourne Big Shortcut was one particular black hole at a redshift of about 10, glimpsed by pairing Webb with Chandra and magnified by a massive cluster of galaxies sitting in the foreground. It looked overmassive in the extreme, a black hole rivaling its entire host, and it was hailed as the first clear fingerprint of a heavy seed. Then, in 2026, other astronomers went back to the X-ray data with fresh eyes and colder skepticism. The signal, they found, was marginal, faint enough that it might be no signal at all, and, tellingly, it refused to sharpen as more observing time was piled on, the way a real source should. The record holder had, quietly, been partly unfound. It may yet prove real. It may turn out to be an ordinary galaxy that only wore the shape of a monster. The jury is still out. Even the sizes are softening. If those little red dot black holes really are 100 times lighter than we first believed, then for a great many of them, the overmassive problem shrinks towards something the models can carry. What stays genuinely hard is the handful of true heavyweights, the billion-sun quasars, that cannot be explained away, and that still somehow had to be built in a terrible hurry. So the black holes were ahead of schedule, and we did not yet know how. But by now, a larger suspicion had begun to gather, bigger than any single object. It was not only the black holes that had arrived too soon. Everywhere Webb turned its eye, the early universe kept looking more finished, more grown, more thoroughly built than a place that Young had any business being. Any one of these surprises, taken on its own, the old picture might have swallowed. A single galaxy grown too large too early is a marvel. A black hole a little ahead of schedule is a puzzle for the specialists to chew on. But they did not arrive one at a time. They came together from every direction at once, and when you stepped back far enough to take them all in, a single shape showed through the noise. The same word, written over and over across the early universe, in 3 different hands. The first hand wrote it in light. Set mass aside entirely. Set aside every argument about how many stars make a given glow or whether a red dot is a monster or a mirage. Just count the bright galaxies. At each step further back in time, ask one plain question. How many luminous galaxies are there, and how does that number compare with what the models had promised? The models had been clear enough. Bright galaxies should grow scarce very quickly as you go earlier, thinning toward almost nothing by the first few 100 million years. Instead, they stubbornly refused to thin. At a redshift of 10, Webb was finding something like 10 times as many bright galaxies as the models had left room for. By a redshift of 14, out at the very edge of sight, it was closer to 180 times as many. And this, of all the surprises, is the one that will not go quietly, because it is built on light, not on inference. You can argue for years about how much mass hides behind a given glow. We have watched exactly that argument unfold, but you cannot argue with how much light actually landed on the mirror. The photons are the photons. The early universe was simply pouring out more starlight sooner than anything in our understanding said it could. That excess is real, and it is not going anywhere. The second hand wrote the word in stillness. Not all of the early galaxies were blazing. Some had gone quiet, red and dead, their star-making finished. Astronomers call such a galaxy quiescent, and finding one in the young universe is its own kind of impossibility. Take one that Webb confirmed at a redshift of about 7, some 700 million years after the beginning. It was massive, a proper galaxy's worth of stars, and it had stopped. By the time its light reached us, it had already switched off its star formation sometime in the 50 to 100 million years before and settled into a long red silence. Galaxies like it proved to be more than 100 times as common at that early moment as any model would permit. Sit for a moment with what that requires. This galaxy had to do two impossible things in succession. First, it had to build a great mass of stars, quickly in the first few 100 million years, the very trick we had already been failing to explain. And then it had to do the opposite, just as quickly, to shut the whole engine down, to stop making stars entirely, while the universe around it was still young and still brimming with gas. It is like watching a city throw up every one of its buildings in a frantic rush, and then, while it is still barely more than a town, halt all construction for good and go completely still. The third hand wrote in shape. The young universe was supposed to be a violent place, galaxies still gathering, still colliding, still churning, their gas hot and disordered, nothing yet settled into calm. Order was meant to come late, only after billions of years of turbulence had a chance to die away, and yet Webb kept finding order early. It found rotating disks, broad, flat wheels of stars and gas, all turning together in the same smooth direction, so orderly that the sheer speed of their spin drowned out the random jostle of individual stars. As far back as 700 million years, when disks that calm were not supposed to be able to exist. Later, though still far earlier than the models allowed, it found the full furniture of a grown galaxy, sweeping spiral arms and the long straight bars of stars that run through the hearts of spirals like our own. And it confirmed some of these not by their look alone, but by tracking how their stars and gas genuinely move, so that no chance arrangement could be mistaken for a real spinning structure. One giant spiral, nicknamed the Big Wheel, was already turning 2 billion years in with 5 or 6 times the mass of the entire Milky Way. Another, a barred spiral so like our own galaxy that it could almost pass for its portrait, sits at a comparable distance. Though that one remains for now only a candidate, its distance judged from colour rather than confirmed. The ordered galaxies, you know, the graceful spirals, the calm, bright wheels, the kind of galaxy you would recognise from any photograph of the modern sky, were arriving long before there had been time to settle into such grace. A calm whirlpool turning quietly in what was supposed to be whitewater rapids. So there it was at last, the whole shape of it seen plainly. Too bright, too heavy, too grown up, too orderly, and every last part of it too soon. A young universe that kept, in every way we knew how to look at it, behaving like an old one, pouring out more light than it should have, building more mass than it could have, finishing its galaxies and settling them into shape long before the schedule ever allowed. It was, taken all together, the most interesting problem in the sky, and it pressed a single hard question, the one that every coming answer would have to reckon with, the question that separates a true revolution from an honest mistake. Of all these surprises, which were the universe telling us something new and real about itself, and which were only telling us that we, in our eagerness out at the edge of sight, had misread the light? There comes a moment, in any real mystery, when the thrill has to give way to the work. We have spent this while inside the thrill, falling down the ladder into the dawn, meeting the galaxies too bright and too heavy, the black holes grown before their galaxies, the dead cities and the calm early wheels. That astonishment was real, and it was earned. But astonishment is not an answer, and the people whose task it is to understand these things could not stay astonished forever. Sooner or later they had to sit down and cool off and do the harder, less glamorous thing, say precisely what the problem was, because a problem carelessly stated can only be argued about, never solved. And the crisis, as it had been shouted from the rooftops, was carrying 2 small words that were each doing far more work than any one word should. The whole fog, it turned out, was hiding inside them. The words were big and broken. Take big first. When people said these galaxies were too big, the word was quietly doing 2 separate jobs with a hidden seam between them. One job was light, too many bright galaxies too early. That is a statement about how much glow arrived at the mirror, and it is about as firm as a measurement ever gets. Count the shining points, set the count against the models, and the count comes out too high, 10 times too high at a redshift of 10, nearly 200 times too high out at the very edge. None of that leans on any theory of what the galaxies are made of. The other job the word was doing was mass. Too much matter, too many stars. And that is a wholly different sort of claim, because mass is never something a telescope measures. No instrument ever built weighs a galaxy. What the telescope catches is light, and to turn that light into a mass, someone must first tell a story about it. How many stars, of what kinds, at what ages, dimmed by how much dust it would take to shine in just that way. That story is a model, and a model can be wrong even when the light it is fed is exactly right. We have already watched that very thing happen. A single black hole's glare red as the massed shine of 100 billion stars, and the mass dissolving the instant the light was read correctly. So the first thing that precision buys us is a clean split. The excess of light is measured and stubborn and real. The excess of mass is inferred and soft and wide open to doubt. They were never one crisis, they are two, and they do not rise or fall together. Then there is broken, the more dangerous word of the pair. To say the universe was breaking could mean an earthquake, or it could mean a leak, and the two are so different in scale that letting them share a word does real harm. The earthquake version says the framework itself is wrong. The Big Bang, the expansion, the recipe of ordinary matter and dark energy, the whole patient account of how gravity draws structure out of the dark. To break that would be to rewrite the floor the physical world stands on, the kind of thing that comes, if it comes at all, once in a century. The leak version says something far humbler and far more common in the long history of science, that the framework is sound, but the workings we bolt onto it are incomplete. In particular, the tangled, half-understood business of how a cloud of gas inside a galaxy actually turns itself into stars. That is not the foundation of physics, it is the plumbing, and the plumbing gets revised all the time. The gap between those two readings is exactly the gap between saying the laws are broken and saying we misjudged the builders. Almost all the noise had assumed the earthquake. The evidence, looked at with a level eye, kept pointing at the leak. To see why, return one final time to the ceiling. A galaxy cannot make more stars than its raw material allows. It draws ordinary matter, that 1 part in 6 of everything, down into itself, and out of that gas it builds. The very most it could ever make is fixed by how much gas it managed to gather. Convert every last atom into a star, waste nothing whatsoever, and you have reached the ceiling. That ceiling is a number the framework hands down, and it does not bend. You cannot raise more house than you have bricks for, but no builder lays every brick. In the universe around us, galaxies are wasteful, clumsy things, turning only 1/10 or 1/5 of their gas into stars before blowing the rest back into the dark. How near a galaxy comes to its ceiling is not a question of cosmology at all. It is a question of efficiency, of the craft of the building, and efficiency belongs to astrophysics. Now the stress test that had frightened everyone reads in a different key. To build the very heaviest of the universe breakers that arithmetic had found, the early cosmos would have needed to work at something close to 99% efficiency, to take almost every brick it possessed and lay each one flawlessly. It is a staggering figure, but look hard at what it is not. 99 is not 101. It does not demand more bricks than the framework can supply. It demands only that the builders were almost unaccountably good at their trade. The universe breakers, even at their most extreme, had their faces pressed to the ceiling, but they were not quite breaking through it. And that reshapes the whole meaning of the word impossible. It never truly meant that a galaxy held more matter than the cosmos could provide. That really would have cracked the world open. It meant that a galaxy seemed to have used the matter it had far, far better than any builder we had ever caught in the act. That is a strange and heavy thing to ask of the young universe. But it is a question about the builders. It is not a question about the bricks. Stated with that much care, the whole terrifying crisis quietly shrinks, and oddly grows more interesting for the shrinking. It had never really been the claim that the Big Bang was wrong. Underneath, it came down to three possibilities, and only three. Either we had misread the light, and there was simply less here than there had seemed, or the early universe truly did forge its stars with an efficiency nothing in our experience had prepared us for, or, most likely of all, some real measure of both. That is the whole distance between the rules being broken and the builders being misjudged, and it is worth every bit of the trouble it takes to keep the two apart. And once the question is set down that plainly, the path forward stops being a matter of taste. It is not settled by arguing the models more loudly, nor by reaching for whichever answer thrills you most. It is settled the one honest way there is, by going back to the sky and looking again, harder and longer and with a colder and far more skeptical eye, and letting the universe itself decide which of these astonishments can survive a second unforgiving look. The checking, when it came, did not make headlines the way the breaking had. There is a cruel imbalance in the way discoveries travel. A galaxy that breaks the universe races around the world in an afternoon. The quiet paper, 2 years later, showing it did no such thing, arrives to an empty room. But the quiet papers are where science actually lives, and in the years after the first alarms, they came steadily. The second looks, the harder measurements, the colder eyes. One by one, they returned to the astonishments and asked the only question that finally matters. Not, is this exciting, but is this true? And one by one, a great many of the impossibilities began, gently, to come apart. The deepest record of them all was the first to fall, and it fell the hardest. In the very first week of Webb's data, in the summer of 2022, a galaxy surfaced at what looked like a redshift of 16. If it held, it was the most distant object anyone had ever seen. Its light released a mere 235 million years after the Big Bang, deeper into the dawn than the ladder had yet reached. For a brief, giddy while, it was the record, written up and celebrated as the new edge of sight. Then someone took its spectrum, spread its light out properly, and read it instead of guessing from its color. And the record simply evaporated. The object was not at the dawn of time at all. It was an ordinary galaxy at a redshift of about 5, sitting comfortably 1 billion years into cosmic history, thick with dust and busy making stars. Its whole disguise had been a cruel coincidence of light. Bright emission from its glowing gas, combined with the reddening of all that dust, had counterfeited the precise color signature of a galaxy at the edge of the universe. The color had lied, exactly and convincingly. A hunch drawn from a few smudged filters had mistaken a middle-aged galaxy 1 billion years old for a newborn one, barely 200 million years past the beginning, off by the better part of the universe's first age. And here is the part that redeems the whole embarrassment. The trap had been seen coming. Only weeks after those first images arrived, while the record was still being toasted, another team had published a warning. Watch out, they said, for dusty galaxies around a redshift of 5, because they can wear the colors of the first galaxies almost perfectly and fool you. The field had marked the pit before anyone stepped into it. So, when the spectrum came and confirmed the warning, it was not a humiliation. It was the whole system working exactly as it was meant to. Nor was it a lone slip. Once the spectra started coming in, somewhere between 1/5 and 2/5 of the very deepest color-picked candidates turned out to be interlopers of just this kind. near galaxies wearing the mask of ancient ones. Then came the harder reckoning, the universe breakers themselves. Recall that all 6 of them had been candidates, their staggering weights read from color and never yet tested against a spectrum. So astronomers ran the test. They took spectra, and they brought in Webb's mid-infrared eye, its longest wavelength instrument, which sees the part of a galaxy's glow that most honestly betrays its true stellar bulk. And they weighed the 6 again, properly this time. The weights fell. They fell for 3 reasons, and we have already met the first. Some of these massive galaxies were not crowds of stars at all, but the little red dots, a shrouded black hole's glare, counted as the shine of 100 billion suns. One of the original 6 was pinned down as precisely that, a feeding black hole sitting nearer than its distance had claimed. The second reason was subtler. In others, the bright emission of young, furiously star-forming gas had been mistaken for the mellow light of an old and massive population padding out the count. And the third was simply better light. With the mid-infrared folded in, the guesswork tightened and the sheer number of supposedly impossible heavyweights dropped by about half. For the few candidates studied most closely, the revised masses came back as much as 100 times smaller than the headline had claimed. When the counts were redone with all of this accounted for, the massive galaxies of the early universe settled back, more or less, into what the standard picture could carry. A mild excess lingered. The young cosmos was still a touch more productive than expected, but the catastrophe was gone. As one of the astronomers who redid the arithmetic put it, plainly and a little wryly, none of them turned out in the end to be so massive as to break the universe. So the loudest and most frightening part of the whole affair, the impossible masses, the near-perfect efficiency, the galaxies that could not be, largely dissolved. And notice how it dissolved. Not because the universe proved obedient after all, and not because some grand new law rode in to save it. It dissolved because we had, in our first eager glimpses at the ragged edge of sight, simply read too much into too little light. The map had been drawn too boldly, and the land, once we finally surveyed it with care, argued back. It is worth stopping for a moment on what that actually was, because from the outside it can look like failure, and it is very nearly the opposite. A field announced spectacular results, in good faith from the best data it had, and then the same field, often the very same people, sometimes in papers you can almost hear exhaling with relief, went back and checked and quietly talked its own discoveries down. It demoted its own record. It unmade its own headlines. That willingness to turn a cold eye on your own most thrilling result and to say the 2 hardest words there are, "We were wrong," is not a flaw in the method. It is the method. It is the whole reason any of this can be trusted in the first place. The courage to undiscover a thing is exactly the point. And so, one at a time, the impossible galaxies became merely astonishing, which is a far more comfortable thing for a galaxy to be. But not all of them went quietly. When the dust had cleared and the false alarms had been swept away, the interlopers sent home, the black holes subtracted, the masses brought gently back to Earth. One surprise was still standing in the middle of the room, untouched by any of it, and it had no intention of leaving. The survivor was light. When all the false alarms had been cleared away, the interlopers unmasked, the black holes subtracted, the swollen masses brought gently back to something the models could hold. One plain fact was still standing exactly where it had begun, and nothing in the great correction had laid a finger on it. There were too many bright galaxies, too early, at a redshift of 10 times more than the models had allowed, out at the very edge of sight, closer to 200 times more. And it survived because, from the very first, it had never been a claim about mass at all. It was a claim about light, about how much glow had actually landed on the mirror, and you cannot argue a photon out of existence. The early universe really was pouring out more starlight and pouring it out far sooner than anything in our understanding said it could. So this one was real. The question was what it meant. And here the story takes its most satisfying turn, because the answer, when it finally came into focus, was not a broken universe and not some undiscovered force. It was something quieter and, in its way, far lovelier. The early cosmos had simply been better at making light than we had ever thought to let it be. Our models had been too cautious, too stingy about what the first few 100 million years were capable of. The universe was not breaking a rule. It was being more generous than the rule had imagined. There turned out to be several ways it managed that generosity, and the first has to do with breaks. Star formation, left to itself, tends to put a stop to itself. As soon as the biggest new stars catch fire inside a cloud of gas, they begin to fight their own birthplace, pouring out fierce light and wind, and then, after a few million years, dying in supernovae that heat the surrounding gas and blow it apart. That violence scatters the raw material before most of it can ever become stars, and star-making sputters out. It is the reason galaxies today are such clumsy, wasteful builders, turning only 1/10 or 1/5 of their gas into stars before the rest is gone. The breaks come on early, but in the young universe the gas was different. It was denser and it was pristine, very nearly pure hydrogen and helium, without the heavier elements that in later ages help gas hold itself apart. Gas like that can collapse astonishingly fast, in under 1 million years, and that speed changes everything, because the supernovae, the breaks, take a few million years to arrive. So there is a window, brief and decisive, in which a cloud can fall together and convert itself into stars wholesale before the first explosion ever goes off. The stars ignite faster than the blasts that would have stopped them. Pour a cloud into that window, and it does not squander 9/10 of itself. It spends nearly all of itself in one unchecked rush of ignition. A galaxy running like that would blaze. But the universe had a subtler trick than sheer efficiency. One that does not even require a galaxy to hold more stars, only to be caught at the right instant. Suppose the early galaxies did not make their stars at a steady, even pace, but in bursts, long quiet spells, then sudden furious episodes of ignition, then quiet again. A galaxy in the throes of a burst flares far brighter than its ordinary self, and since it is the brightest galaxies we count when we tally the light, we are forever catching galaxies in the act of flaring. Many of the extra bright ones may be perfectly ordinary galaxies, snapped mid-flame. The early universe would flicker the way you have watched a fire flicker as it catches, one patch of the dark blazing up, then dimming, while another patch takes light somewhere else. And from far enough away and long enough ago, all that flickering reads as a sky with far too many fires burning at once. Beneath both of these ran two quieter effects, and they leaned the same way. The first stars, born out of that pristine gas, may have been born bigger, on the whole, than stars are born today, and a large star burns hotter and enormously brighter than a small one, so a given weight of stars, if the mix runs heavy, throws off far more light than the same weight would now, and there was less to dim that light. Dust, the fine soot that reddens and darkens starlight, is itself built from heavy elements, which take generations of stars to forge, so the earliest galaxies had barely any, and what little dust did form, the young galaxies seem often to have swept clean away. So the early starlight escaped almost unhindered, clean and blue, none of it lost to soot. We saw exactly that in the very first galaxy we studied together, the one already glowing at the edge of sight, luminous and blue, and remarkably free of dust. Brighter stars, and nothing much standing in the way of their light. No single one of these has yet won the argument, and it is only honest to say so. Whether the early universe was mostly running its star-making faster, or mostly flickering in bursts, or mostly just born brighter and cleaner, is still being worked out, and the truthful answer is very likely some measure of all of them together. But the shape of the answer is no longer in doubt, and it is both a relief and a quiet wonder. The first galaxies never needed a broken cosmos to explain them. They needed only a universe that made its light more freely, more eagerly, more generously than our careful, cautious models had ever dared allow. The first light, it turned out, was simply more willing to shine, if you like, than we had given the young universe credit for. And that lays the loud crisis to rest, the one that had filled the headlines and rattled the seminar rooms. But it leaves a quieter question standing in its place, and this one does not clear away so easily. If the early galaxies were not, in the end, the crack running through our picture of the universe, then is there a crack at all? And if there is, where has it truly been hiding? There is a version of this story that could end right here, and it would be comfortable, and it would be a lie. It would go like this. The early galaxies frightened us. We looked closer. The fright dissolved. The standard picture held, and all is well. Every part of that is true except the last three words. Because all is well is not something an honest account of the universe is ever allowed to say. Least of all one that calls itself as we understand it, a title that is really a promise to tell you where our understanding runs out. And our understanding does run out. There is a genuine crack in our picture of the cosmos, deep and stubborn and entirely unexplained. It simply is not the one everyone had been pointing at. To find it, you have to look away from the first galaxies altogether and toward a single number. The universe is expanding, every galaxy drifting from every other, the whole of space slowly swelling as it has since the beginning. And that expansion has a speed, a rate you can measure, a number that says, in effect, how fast the universe is flying apart. It is one of the most important numbers in all of science, and we have two entirely separate ways of pinning it down. The first way reaches back to the beginning. Take that ancient afterglow, the oldest light, set free 380,000 years in. Read the faint pattern frozen into it. Feed it through the standard account of how the universe has grown ever since, and out comes a prediction for how fast the cosmos ought to be expanding today. That number comes to about 67. The second way ignores all of that and simply measures the expansion directly, here and now, in our own neighborhood. You find stars whose true brightness you already know, and exploding stars bright enough to be seen across enormous distances, and you use them as mile markers to judge how far away nearby galaxies lie and how quickly they are receding. Climb that ladder of distances rung by patient rung, and you read the expansion straight off the sky. That number comes to about 73. They are measuring the same thing. It is the same universe, the same expansion, the same quantity in the same units. And the two answers, 67 and 73, refuse to agree by nearly 1 part in 10. For a while it was easy to hope the gap was some small mistake that sharper data would close. It has done the opposite. As both methods have grown finer and more careful, year over year, the disagreement has not faded. It has hardened until it now stands past what physicists call 5 sigma. The same demanding bar a genuine discovery has to clear, the point beyond which a result is simply too strong to be a fluke. There are only 2 ways to read a standoff like that, and both are unsettling. Either one of our 2 most careful methods for weighing the universe hides a flaw so subtle that a decade of the sharpest minds in the field cannot find it. Or the universe is quietly doing something somewhere between that ancient afterglow and this present sky that our best account of it does not contain. There is no comfortable third option. That is the real open wound in cosmology, and it has a name: the Hubble tension. Nobody yet knows what it means. It could still conceivably be a subtle error lurking in one method or the other, though that hope grows thinner with every recheck. Or it could be the sign that our standard account is missing something real, some new ingredient active in the young universe that we have not yet written into the recipe. One hypothesis, and it is only that, imagines a brief early pulse of something like the dark energy that pushes the universe apart today, switching on and off before that afterglow was ever released, quietly resizing the ruler the first method leans on. It is an ingenious idea. It is also in trouble. The same pulse that would ease the disagreement over expansion tends to worsen a second, milder one, a quieter argument over just how clumpy the universe is, how thoroughly its matter has gathered into clusters, and the largest galaxy surveys we have since made have not been kind to it. So even the leading candidate for new physics is contested, and the honest scorecard reads, a real crack and no agreed explanation for it. And here is the part that matters most for our story, the part that takes genuine discipline to say plainly. The first galaxies are not this crack. When the excitement was at its peak, some had hoped to enlist them, to point at the too bright dawn and the quarrel over expansion and say, look, two symptoms of the same hidden new physics. But the link never held. The early galaxies, as we have watched, gave up their secret to ordinary astrophysics, with no new ingredient required at all. The door to deeper physics is genuinely open, and the Hubble tension is the thing standing in the doorway. The first galaxies, in the end, were never the ones knocking. Most cosmologists in 2026 do not count them among the evidence against the standard model, and that restraint, that refusal to press a thrilling object into service for a case it cannot actually make, is exactly the discipline this whole episode had been quietly teaching. Which leaves us in the honest place, the grown-up place, the one this whole long night has been walking toward. Not everything is solved, not everything is broken. Our picture of the universe works astonishingly well, passing test after test after test. And it carries, at the very same time, one genuine unexplained crack that we can point to with precision, and are honest enough to admit we do not understand. To sit with that, to hold a real mystery in both hands and neither wave it away nor rush to fill it with the first dramatic answer in reach, is a harder thing than either certainty or panic, and a far truer one. The framework held, and with it standing firm beneath us, we can go back at last to the first galaxies, not as a threat to be diffused, but as a gift to be opened. Because their light did not only trouble our models, it did something to the whole universe around them. It set the dark on fire. To understand what the first light did, you have to go back into the dark that came before it. We passed through that dark quickly, earlier in the night, the long stretch after the afterglow, when the universe had cooled and gone quiet, and there was nothing anywhere that shone. But it was not only dark, it was, in a particular way, foggy. All of space was filled, edge to edge, with the plain gas the Big Bang had left behind. Hydrogen, atom after atom of it, each one a single proton holding a single electron. And neutral hydrogen like that has an appetite. It drinks ultraviolet light, the energetic, high-pitched light that can knock an electron loose, swallowing it before it can travel far. So the young universe, though transparent to the gentle glow of the afterglow, was murky to the very kind of light that stars would one day pour out. A fog you could not see, filling everything, waiting in the dark. And then the fires were lit. When the first stars and the first galaxies finally caught, those furious, blazing blue young stars we have spent the whole night chasing, they flooded their surroundings with exactly that ultraviolet light, the light the fog was hungry for. But there was so much of it, and it came on so hard that the fog could not keep swallowing. The energetic light struck the hydrogen and tore its electron clean away, splitting the atom back into the loose proton and free electron it had been in the very beginning. And gas broken apart like that loses its appetite. Ionized hydrogen does not drink ultraviolet the way the whole atoms did. So around each new galaxy the fog began to clear, the light carving out a slowly growing bubble of transparency in the murk, a pocket of clean space with a galaxy burning at its heart. This is the great turning astronomers call reionization, reionizing, because the universe had been split apart like this once before, in its first hot instant, and was now being split a second time, not by heat but by starlight. And it did not happen everywhere at once. It happened the way a fog burns off a valley at dawn, not as a single curtain lifting, but as a scatter of clearings, opening one by one wherever a fire was bright enough. Each early galaxy cleared its own bubble. Had you been there to watch, you would have seen the clearings widen and press against their neighbors and merge. Two becoming one becoming a vast connected clearing, until, after a long slow while, the last dark pockets of fog between them thinned away, and the whole universe stood clear from end to end. A long slow while, and this is where Webb rewrote the story. It had once been thought that the clearing was a relatively late and tidy affair. Instead, the telescope found the fires guttering to life startlingly early. In the light of a galaxy at a redshift of 13, barely 300 million years in, there is a signature that could only have reached us if the fog immediately around it had already been burned clear, a bubble open at the very dawn. From those first scattered clearings the process ran on, gathering pace through a redshift of 7 or 8, when the universe was roughly half cleared, and it did not finally fully finish until a redshift of about 5, more than 1 billion years after the beginning. Not a curtain lifting then, but a sunrise that took 1 billion years, the universe slowly, patchily, kindling itself into transparency. And now the too bright dawn that had so troubled us comes back around, wearing a different face. Because all that excess early light, the generosity we had struggled to explain, the galaxies burning brighter and sooner than any model allowed, was never merely a puzzle for our theories. It was the fuel. Those abundant early fires were precisely what the fog needed. The surprise that had looked so much like a crisis turns out to have been the very engine that lit the universe. It even turned out to be a puzzle of plenty. When astronomers tallied how much ionizing light the early galaxies were pouring out and asked whether it was enough to clear the fog, they got an almost comic answer. It was too much. By the raw numbers, the young galaxies made something like 4 times more of this light than the job required. Enough to have cleared the sky far too fast and finished it far too early. For a while this looked like yet another crisis. It is settling now, the same quiet way the others did. The catch is that most of a galaxy's ionizing light never escapes the galaxy at all. It is drunk back down by gas close to home, long before it can reach the open fog, so only a small fraction ever gets out to do the clearing. Fold that in, and the budget balances, and the billion-year timeline holds. Whether the galaxies managed the whole job alone, or whether the faint, early black holes we met lent a hand, is still argued over. But the sky got cleared, and it was the first light that cleared it, which leaves a strange and lovely inheritance. The universe you live in is a cleared one. That fog which once filled all of space, edge to edge, and would have veiled the deep sky behind a haze the sharp light of galaxies could not pierce. It is gone, burned away over 1 billion patient years by the light of the first fires. The clearing was not there at the beginning. It was made, and the universe handed that clarity down to everything that followed after. The whole long transparent stage on which every later star and galaxy and world would go on to live out its life, including, at the very end of that long line, you. And yet, for all of it, these first galaxies were not truly the first thing to shine. Before them, before there were galaxies at all, back in the deepest pristine dark, there had already burned a single, earlier generation of stars, a generation that made the first light of all, a generation we have still never seen. Everything else in this long story, we have at least glimpsed. The record-breaking galaxies, the little red dots and their hidden black holes, the fog burning back into a clear sky, all of it has crossed a mirror and left its mark. The first stars have not. They are the very beginning of the whole account, the thing that made everything after them possible, and they are the one part of it we have never actually seen. And yet we can describe them in startling detail, because the emptiness they were born into tells us what they had to be. Astronomers call them population 3, and there is a small charm in the name, because it runs backward. The stars most like our Sun are population 1, the older planar stars are population 2, and these, the very first of all, were handed the last number, simply because we only worked our way back to them at the end. Think about what the young universe had to build with. Only the two lightest elements, hydrogen and helium, the plain gas of the Big Bang, and nothing heavier anywhere. That absence matters more than it sounds, because it is the heavier elements that let a gas cloud cool. As a cloud collapses under its own weight, it heats up, and to keep falling it has to shed that heat. Heavier atoms are wonderful at radiating warmth away, and a cloud laced with them can cool and fragment and break into a scatter of small stars, stars like our Sun. The first clouds had none of that. They could not cool efficiently. They stayed hot as they fell, and hot gas refuses to break into small pieces. So instead of shattering into many modest stars, each cloud collapsed, more or less whole, into one or a few enormous ones, stars of tens, of hundreds, in the very largest cases, perhaps nearly 1,000 times the mass of the Sun. Picture such a thing. A star that size is nothing like the gentle yellow sphere that warms us. It is a monster of raw hydrogen, so massive and so hot that it burns blue-white, savage with ultraviolet light, blazing thousands of times brighter than the Sun through every moment of its life. And it does not have long. A star burns faster the larger it is, and these were the largest there have ever been, so they tore through their fuel in a geological instant, a few million years, and then gone. The first fire the universe ever lit was so fierce that it was over almost before the universe had finished being young. But in that brief life, each of those giants did something the cosmos had never managed before. It made the heavy elements, every atom in existence weightier than helium, the carbon in every living cell, the oxygen in every breath, the iron that reddens blood, the calcium that stiffens bone. Every one of them was forged inside a star, and the very first of them were forged inside these. And when the giants died, they handed their harvest back. The most massive did not collapse quietly. A whole range of them detonated so completely that nothing at all remained behind. No cinder, no core, no black hole. The entire star torn apart and flung outward, salting the surrounding dark with the first heavy atoms it had ever held. The very largest of all may have gone the other way, folding straight down into black holes, and those, quite possibly, were the heavy seeds we went looking for earlier. The running start that let the first monstrous black holes grow so impossibly fast. So the lineage runs unbroken all the way down. The first stars made the first heavy atoms. Those atoms let a second generation of stars form and cool and break into smaller, longer-lived things. And somewhere down that chain, billions of years on, a modest yellow star gathered a disk of enriched dust into planets. And on at least one of them the atoms went on arranging themselves into ever more elaborate things, until here you are, listening in the dark. The first stars you will never see are the reason the calcium in your bones exists at all. You are built, atom by atom, out of an inheritance they began, passed down hand to hand across 100 generations of stars. And here is the ache at the heart of it. For everything we can say about them, we have not, as of tonight, confirmed a single one. Not one. They remain a prediction, beautifully worked out, hunted with everything Webb has, and still uncaught. The difficulty is knowing one when we finally see it. What we search for is a very particular fingerprint, the glow of helium lit in the fierce way that only the hottest stars can manage, and beside it nothing at all, no trace of any heavier element whatsoever, the pure signature of gas never once touched by an earlier generation. The best candidate anyone has found sits right beside a galaxy we met early on, GN-Z11, a small separate knot of light, nicknamed Hebe, showing precisely that, helium, blazing, and not a metal in sight. Astronomers have now confirmed that the knot is real and genuinely free of heavier elements. What they cannot yet confirm is that it is stars, a hidden black hole of exactly the kind we have learned to be so wary of, could counterfeit that same clean glow. The first stars, or another black hole in disguise, the argument is live and honest and unfinished. Other candidates flicker at the very edge of detection, a faint clump magnified by a chance alignment of gravity here, a strange metal-free smudge there, each one tantalizing and not one of them certain. It is a fitting place for the deepest part of the story to rest. The very first light of all, the thing that began everything, that seeded the elements you are made of, is the one thing still just out of reach. A ghost caught only in rumors at the far edge of what we can see. We have not found the first stars yet, but we have not stopped looking. And even now, we are building the eyes that finally might. Before we look ahead, it is worth asking how we have managed to see as far as we already have, because a single telescope, however extraordinary, has limits, and Webb has been quietly cheating past its own with two very old tricks. The first is to borrow gravity. Scattered across the sky are great clusters of galaxies, thousands of them bound together, holding so much mass that their gravity bends the very space around them, and light passing through that warped space is bent and gathered and magnified exactly as it would be by a lens of curved glass. A cluster like that becomes a natural magnifying glass, hung in the sky for free, brightening and enlarging whatever unlucky galaxy happens to lie directly behind it. The image that comes through is often warped for the trouble, a far galaxy smeared into a long luminous arc, or split into 2 or 3 curved copies of itself, bent around the cluster like light through the base of a glass. But warped and doubled is a small price for magnified, and magnified is how you reach the otherwise unreachable. Some of the faintest, most distant things Webb has found, including that lonely candidate for the first stars, were only within reach because a cluster in the foreground lent its gravity to the task. Astronomers have learned the useful ones by name, the way a fisherman learns the good waters. A vast, cluttered cluster nicknamed Pandora, the one that filled Webb's very first deep image back at the start of the night. The second trick is simply patience. Choose a patch of sky, one of a handful of small, much-studied windows the great surveys return to again and again, and stare. Not for minutes, but for hundreds of hours, letting the faintest trickle of ancient light gather, photon upon photon, until what began as blank dark fills with galaxies. Depth, in this game, is mostly a matter of how long you are willing to hold still. But both tricks have their ceilings. The magnifying clusters are rare, and you must take whatever happens to sit behind them. The deep fields are tiny, each one a keyhole, and the rarest, brightest early giants can hide forever in the vast reaches of sky between the keyholes. And Webb, for all its genius, is one eye, doing one kind of seeing. It will not be looking alone for very much longer. 3 new eyes are coming, and each is built to reach past a different one of those limits. The first is a matter of width. A telescope named for Nancy Grace Roman, launching almost as we speak, carries a mirror no larger than Hubble's, but it takes in a piece of sky around 100 times bigger in a single glance. Where Webb peers through keyholes, Roman will map vast fields at a stroke, cataloguing millions of galaxies and sweeping up the rare early giants that the narrow surveys were always going to miss. It is the wide net to Webb's fine hook. Roman will find the extraordinary objects in bulk and mark them, so that Webb and the others can turn and study them one at a time. The second answers a different hunger, for light itself. On a mountaintop in the Chilean desert, engineers are assembling a single mirror 39 meters across, an eye so enormous it will gather more starlight than any telescope ever built on the ground or above it. That flood of light is what it takes to do the very hardest thing, to spread the feeble glow of the faintest, farthest galaxies into a full spectrum, and read from it their chemistry, their motion, their true nature, where Webb can often manage only a faint portrait. One of its instruments is being designed with a single hope in mind, that it may be the first thing able to confirm beyond argument a true first star, to read that untouched fingerprint at last and lay the ghost to rest. It should open its eye near the end of this decade, and the third of the new eyes does not gather light at all. Out across the deserts of Australia and South Africa, a small army of radio antennas is being wired together into one vast instrument, tuned not to starlight, but to the faint radio whisper that hydrogen itself gives off. With it, we will be able to map the fog directly, to watch the neutral hydrogen of the young universe as rionization ate its way through it. And more than that, because it listens for the gas and not for the stars, it can hear back past the first stars entirely, into the true dark ages, that long silent stretch before anything shone at all. It is the one way we have of sensing the age no ordinary telescope can ever see, for the simple reason that there was nothing there yet to give off any light. Its first faint images have already begun to arrive. Between the 3 of them, one to find, one to read, one to hear the dark, the early universe will soon have very few places left to hide. So the map is unfinished, and it is meant to be. That is not a failure of the work, it is the shape of the work. Each generation grinds a finer mirror, or dreams up a stranger one, answers the questions it can, and hands the rest forward to the eyes that come after. A long relay, running for centuries, no single runner ever meant to reach the end. What is remarkable, standing here tonight, is how near some of the answers already are. Whether the first stars truly burn in that clump beside GN-Z11, what really cleared the fog, how the first black holes cheated their way to such size, these are not riddles for some distant century. The instruments that will settle them are being bolted together right now, and the answers are already on their way. Some of them, very likely, will arrive within your own lifetime. You may yet live to hear the first stars confirmed. And so the story is not finished. In truth, it has barely begun, which leaves only one last thing to do tonight before the lights go all the way down. Not to ask what else is out there or which new eye will find it, but to ask quietly what all of this light and all of this looking has really been for. It is a fair question to end on, and it is worth sitting with, because it does not have the kind of answer you can write down in a single line. Look back over the ground we have crossed tonight, not the particulars of it, the redshifts and the instrument names and the arguments, but the plain shape of the thing. We took the coldest, most patient eye our species has ever built, and we carried it 1,000,000 miles out into the dark, and we pointed it at the faint red edge of everything. And then we fell, rung by rung, deeper and deeper, down a ladder into the first light of the universe, past galaxies whose glow had been travelling toward us since before the sun had caught fire, before the earth had gathered itself out of dust, before the atoms that would one day become you existed anywhere at all. We fell so far back that we watched the universe grow younger as we went, until we were seeing it as a newborn, only a few 100,000,000 years old. And what we found waiting down there did not match the map we had carried into the dark. The dawn was too bright. It was too crowded and too finished, and too soon. Galaxies that were supposed to be faint, struggling sparks were instead blazing and grown and already seasoned with the ash of stars that had lived and died before them. And for a while, you will remember the feeling. It looked as though the universe had broken its own deepest rules, and the word went round the world that our whole account of the beginning might be wrong. And then we did the slow, unglamorous, honourable thing. We checked. We took the thrilling results, the ones that had raced across the world in an afternoon, and we held them up to a colder and more sceptical light, and we let the ones that could not survive it quietly fall away. The record breakers that turned out to be nearer galaxies wearing a clever disguise. The impossible masses that shrank the moment we read the light properly instead of guessing at it. We watched a whole field of careful people turn a hard eye on their own most exciting discoveries and demote them and unmake their own headlines and say the two hardest words there are, "We were wrong," not as a defeat, but as the very thing that makes the work worth trusting at all. And when the dust had settled, the terror had gone out of it, and something far better had taken its place. The universe was not broken after all. It was only more generous than we had let ourselves imagine, more willing to make light and to make it sooner than our careful, cautious models had ever dared allow. The surprise that had frightened us so badly turned out to be a gift in disguise. Those first extravagant fires, burning brighter and earlier than they had any right to, were the very thing that lit the cosmos, that burned away the long fog of the young universe over 1,000,000,000 slow years, and cleared the sky into the deep, transparent dark you are lying beneath right now. And beneath even those first galaxies, we caught the faintest rumour of something older still, a first generation of stars, enormous and blue and long since gone, that we have never yet managed to see, and are even now building new eyes to find. That was the story, but it was never quite the answer to the question, because you can follow every step of it, every galaxy, every correction, every clearing, and still find yourself lying here at the end of the night quietly asking why any of it should matter to anyone at all. What is it to us, so impossibly far downstream, that a galaxy we will never touch and never reach was a little too bright, a little too soon? The answer, in the end, is much closer than the galaxies. It is as close as the breath you are taking right now. Think back to that one galaxy at the very edge of sight, the one already glowing with oxygen when the universe was less than 300,000,000 years old, the one that so astonished the people who found it. That oxygen was not some curiosity locked inside a distant object. It was the same oxygen you are breathing, this very moment, in the quiet of your dark room. There is no other kind. Every atom of it in all the universe was forged in the core of a star and flung out into space when that star died. And the first of it was made inside the first stars of all, those brief, enormous, unseen giants that lived and died before there were even galaxies to hold them. And it does not stop with the oxygen, the carbon that is the frame of every living thing, the iron that moves through your blood and turns it red, the calcium that stiffens your bones and lets you stand upright and lie down again. Every one of those atoms carries the same history. None of them existed in the beginning. The Big Bang made only the two lightest gases and nothing more. Everything heavier, everything you are built from, was cooked slowly inside stars, one generation handing its ash to the next, down and down across billions of years, until at last a little of it gathered around a small warm star and settled into a wet world and stirred and eventually sat up in the dark and began to wonder where it had come from. So when we turn a telescope toward the first galaxies, we are not looking at something separate from ourselves, something out there, on a screen, a story about strangers. We are reading the opening pages of our own biography. The early universe is not a distant abstraction. It is the place your atoms are from. That faint light at the edge of everything is not news of another world. It is the oldest photograph of home. And there is something in that worth holding very quietly before we let the night close over it. For nearly 14 billion years, the universe went about all of this: the forging of the elements, the kindling of the galaxies, the slow assembling of everything there is, with no one anywhere to see it. It made the oxygen and the iron and the light, and there was no eye to catch any of it, and no mind to know that it was happening at all. And then, in the very last thin sliver of that immense stretch of time, on one small world, the matter that the stars had made arranged itself into something that could turn and look back up at the sky it had come from and ask what it was. After all those silent ages, the universe grew an eye. In one small place, it became able to see itself. And when it looked, when it built its finest, coldest instrument and turned that eye on its own beginning, it found the beginning stranger and brighter and harder to explain than it had expected. And here is the whole of it, the thing this long night has really been about. It could have looked away. It could have bent what it saw to fit the map it already trusted and called the matter closed. It did the opposite. It let itself be confused. It said out loud and unashamed that it did not understand. And then it looked again, harder, and let the looking correct it. That confusion, the very thing that gave this story its name, the scientists who could not explain what they were seeing, was never a failure. It was the sound of understanding still being made. To be baffled by your own beginning and to refuse to pretend otherwise and to keep looking anyway, that is not a weakness in us. It is the finest and most honest thing a mind is capable of. A universe that can be surprised by itself and stay humble enough to be corrected is a universe learning, slowly and patiently, to see itself clearly. And we are how it does that. For now, in this small corner of it, we are the part that looks. You do not need to do anything with that tonight. There is nothing here to solve, nothing to finish, no piece of it that depends on you staying awake a moment longer. The light is still coming after all. Even now, as you lie here, the glow of those first galaxies is still crossing the emptiness, still arriving 13 billion years after it set out, patient and unhurried and in no rush at all to be understood. It has waited this long. It can wait a little longer. And you are made of its leftovers. The same old stardust that seeded that ancient light is gathered now into the shape of you, into the warmth of your hands, into the slow rise and fall of your breath, into the quiet weight of your body settling into the dark. You are the first light, grown old enough to lie still and listen to the story of itself. There was never any real distance between you and the beginning. There never could have been. So let the galaxies keep their long, slow journey. Let the astronomers keep grinding their new mirrors. The answers will come when they come, and they will come without you tonight. You have already done the one thing that ever mattered, which was to wonder at it. That is enough. It has always been enough. Let your thoughts begin to loosen now. Let the numbers go. The billions of years, the bright galaxies, the black holes, the fog burning back into a clear sky. You do not have to hold any of it. Let it all drift gently out to where the first light is, and rest there. The universe took nearly 14 billion years to make something that could love it back. Tonight, in this room, that was you. And there is nothing left to do now but breathe, and be warm, and let the old light hold you while you sleep. Rest now. Good night.